All right, let's dive right in. Today, we're going to get to know the family that literally fuels our world, hydrocarbons. I mean, these are the absolute building blocks of modern energy. And trust me, their family tree is pretty fascinating. So, have you ever stopped to think about what the gas in your car, the natural gas in your stove, and shoot, even a lot of plastics have in common? Well, the answer is a single family of molecules. Yep, at their very core, they're all hydrocarbons. Okay, so to really get a grip on how these things work, we've got to start with the absolute basics. Let's lock in the core definition, shall we? You know, the name kind of gives the whole game away, doesn't it? Hydro for hydrogen and carbon for, well, carbon. That's it. These compounds made of just those two elements are the main ingredients in things like petroleum and natural gas. And that, of course, makes them the world's #1 source of energy. So this hydrocarbon family, think of it as having 4 main branches, and each one has its own unique structure and, you could say, its own personality. We've got the alkanes, the alkenes, the alkynes, and the really special ones, the arenes. So let's go ahead and meet each of them. First up, let's meet the simplest, most straightforward members of the family, the alkanes. So why are alkanes called saturated? Well, it's because they're holding on to the absolute maximum number of hydrogen atoms they possibly can. They're totally full up. And it's all held together with simple, single bonds. That formula you see there, that's kind of their universal recipe. So, for example, if you have 2 carbons, N equals 2, right? So you'd need, let's see, 2 times 2 plus 2. That's 6 hydrogens. Easy. Okay, and this is where their structure gets really interesting. I want you to think of those single bonds like little axles that let the molecule twist and rotate totally freely. This freedom creates all these different 3D shapes, which we call conformations. Now, the most stable shape is called staggered, and it makes perfect sense when you think about it. It just gives all the hydrogen atoms the most personal space, you know? It keeps them as far apart from each other as possible. All right, let's move on to the next branch of the family and kick up the complexity a notch. Things get way more interesting when we throw a double bond into the mix. So let's meet the alkenes. Alkenes are what we call unsaturated, and here's why. To create that second bond between the carbon atoms, the molecule actually had to let go of 2 hydrogen atoms. You can see it right there in the formula. It's simpler. They basically have empty seats, room for more atoms to join, and that's exactly why we call them unsaturated. Now this double bond, it's a total game changer. Unlike that free-spinning single bond we saw in alkanes, this one is rigid. It's stiff. It completely locks the molecule's shape in place. And this rigidity creates something called geometric isomers. These are molecules with the exact same atoms, but they're stuck in different 3D arrangements. We call these arrangements cis and trans. And believe me, this difference in shape has real-world consequences. Take the cis isomer, where the main groups are stuck on the same side. That makes it more polar. It has a slight electrical imbalance, which gives it a higher boiling point. The trans isomer, on the other hand, is more balanced, less polar, and it actually has a higher melting point. It's a fantastic example of a core rule in chemistry. Shape is everything. You can have the exact same atoms, but just arrange them differently, and you get completely different properties. Okay. Time to meet the last 2 major players in our family tree. First, we'll check out the one that takes bonding to the absolute extreme with a triple bond. And then, we'll meet the real celebrity of the family, the one that forms this incredibly stable and important ring structure. You can probably see the pattern emerging, right? We went from single to double bonds, and now we arrive at the alkynes, which feature at least 1 carbon-carbon triple bond. This makes them even more unsaturated, and their formula shows it. They've had to ditch another 2 hydrogens to make that super powerful triple bond happen. And at last, we meet the arenes, also known as aromatic hydrocarbons. And if this family has superstars, this is them. Their defining feature is something called the benzene ring. It's a 6-carbon ring that is so uniquely stable, it basically plays by a whole different set of rules from everybody else. This special stability has a name, aromaticity, and it's not just because it's a ring. It's all about how that ring shares its electrons. See, instead of being locked between 2 specific carbon atoms, some of the electrons form this delocalized system. It's like a cloud of charge that's shared equally by all 6 carbons at once. This amazing electron sharing makes the whole structure incredibly stable and really, really hard to break apart. Okay, so we've got a handle on their structures, but as we know, structure determines behavior.
So, the big question is, how do these different family members actually react out there in the chemical world?
And here's where we see a huge difference in their personalities. Think of the saturated alkanes like a bus that's completely full. For a new passenger to get on, somebody else has to get off. That's a substitution reaction. But the unsaturated alkanes and alkynes, they're like a bus with empty seats. Their extra bonds can just pop open to let new passengers on without anyone having to leave. That's an addition reaction, and it makes them way more reactive. Of course, chemists have figured out all sorts of clever ways to build these molecules. What you're looking at here are basically recipes for making alkanes. Take the top one, for example. That's the worst reaction. You can see how it takes two smaller pieces and uses sodium to just stitch them together into one longer alkane chain. These are absolutely fundamental techniques in any organic chemist's cookbook. Now, when those addition reactions happen on alkenes and alkynes, there's a super predictable pattern. It's called Markovnikov's rule, and it's basically a classic case of the rich get richer, but with hydrogen atoms. So picture a double bond where one carbon has more hydrogens attached to it than the other. When a new molecule comes along to be added, where does the hydrogen go? It goes to the carbon that already had more hydrogens to begin with. It's a simple but powerful rule that lets chemists predict exactly how these reactions are going to go. And now for the big plot twist, which comes from our celebrity family members, the Aryans. You'd think, because they're so unsaturated, they would love addition reactions, right? But nope, they hate them. That aromatic ring is so unbelievably stable that the molecule will do pretty much anything to protect it. So instead of breaking those bonds to add new atoms, it prefers to just swap one out on the outside, a substitution. It will fight tooth and nail to preserve that special stability. And what's really cool is that you can actually control the ring's reactivity. It's like having a dimmer switch. By attaching different chemical groups, you can turn its reactivity up or down. The groups you're seeing here are called electron withdrawing groups. Think of them as little vacuums that suck some of that shared electron cloud away from the ring. And with less of that electron richness, the ring becomes way less willing to react. We call it deactivating the ring. Okay, we have to touch on a really critical real-world risk here. For all their importance, some of these compounds are flat-out dangerous. Benzene itself, and many of the bigger molecules made from sticking benzene rings together, are known to be carcinogenic. That means they can cause cancer. The very stability that makes them so useful in chemistry is what can make them so dangerously persistent inside the human body. And all of this brings us to the ultimate question, doesn't it? Hydrocarbons are, without a doubt, the bedrock of our modern world, from the fuel in our cars to the plastics we use every single day. Understanding their family tree, their structure and how they react, that's the crucial first step. But the real challenge for all of us is how do we balance their incredible power against their undeniable risks to our health and to our planet? It's a massive, ongoing conversation, and it all starts with understanding the fundamental chemistry we've just walked through.